Let us talk about the next classification algorithm called k-nearest neighbors. This algorithm is slightly different from the previous classification algorithms that we discussed. And we will talk about how is this going to be different from that. And in fact, this is actually a pretty easy, understandable classification algorithm. So the major difference from k-nearest neighbor with the previous two algorithms that we discussed, including decision tree as well as naive Bayes, are for those algorithms, they are considered what we call eager learners. So what does that mean? That means that when a training data set is given, these algorithms try to build a model based on those training data set. So try to refresh your memories. Decision tree, using the entropy to build up a tree so it looks like a flow chart. Therefore, when unknown data comes in, you will be able to follow the tree and then make the prediction. Probability based, which is like naive Bayes, for every single attribute, looking into the probability of the category for each attribute, and then we multiply all of the probabilities. The one has a higher value is going to be our prediction. So that is a probability based. Again, you will look into the training data set and find all of those values. SVM is something that we will discuss pretty soon. It's going to use a hyperplane, create a hyperplane in the space, and then try to separate the cases, binary case for most of the general scenarios, so that it can make the predictions through those hyperplane. Association classification is a variation of association rules. We will discuss about that. And there are some other rule-based and then classification by back propagation. This is something more like neural networks. If you take the AI class, that's some important topics going to be included. Therefore, all of these things are like traditional, more general scenarios of what we call the eager learners, which means that they try to build a model, build something from the training data set. Unlike what we are going to talk today, which is what we call a lazy learner, is going to be simply stores the training data. What they're trying to do is they are not going to do anything. They just leave the training data over there without doing anything and wait until it is given a test sample. So when a testing data set comes in, it is then using the training data set try to make the predictions based on that. So they didn't build a model at all, which is something that we will discuss today. And therefore, again, the difference between eager learner versus lazy learning is that eager learning is build a model. Lazy learning is not doing anything for those training data set until when they try to make the prediction. Therefore, for lazy learning, there's almost no time in training because it's not building a model at all. They are not using the training data set at all. However, of course, it will spend more time in doing the testing data set so that it will spend much more time in doing the predicting. So you may be interested, what is k-nearest neighbor trying to do? By the name, it's actually trying to find the neighbors of the testing data set and using the neighbors to tell you what is this class for your testing data. So k-nearest neighbor approach is basically using instances represented as a points and then using, let's start talking about Euclidean distance space, and this distance calculation can be changed into many other different distance spaces so that we will follow up those topics in this video or in this topic basically. So let's take a look at this. K-nearest neighbor algorithm. All instances composed to the points in an n-dimensional space. So basically, depending on how many attributes that you have, you will be able to represent that in the space Of course, you can project all of those things into a two-dimensional space or something like that can be performed in our data preprocessing steps. So the nearest neighbor are defined in terms of Euclidean distance as the most traditional methods for the k-nearest neighbor, and the targeted function could be discrete or real value, and basically for instances value, k-nearest value returns the most common value among the k training examples nearest to the testing data that you have. So this k nearest neighbor, the k is a variable over here. If you use k equals to 1, what I'm trying to say is very clear. You find the closest neighbor, and then this testing data set is going to assign to the same class of that closest neighbor. When k equals to 3, for example, then you look at 3 neighbors and then decide what is the corresponding value for this sample going to be. In this figure, you can see that XQ is actually the testing data set that we have. It find out a circle over there indicating that there are 5 elements inside of this circle, indicate k equals to 5. So you can see that in this case, they try to find 5 closest neighbors, finding out that 2 of them are positive case, 3 of them are negative case. If we treat every single neighbor equally, then of course this testing data will be categorized into a negative case in this scenario. So that is like the most simplest way or traditional way of what we call the k nearest neighbor. Simply try to find the neighbors and let your neighbors to tell you what is the class that you are going to be. So let's take a look at some even simpler examples so that you can fully understand. In this space, so saying that we have this space that in this case, and there are several training. This is our training data set, so indicating that, for example, age. This one-dimensional value is the age, and the dots indicating that whether or not this person has a cell phone, for example. So you can see that in this case, the age of 18, 23, 24, 25, 30, these are the cases that have the cell phone. And here is a special case over here, so we can include that as well. 11, age of 11, maybe the kid has some need or something, that he also have a cell phone, fully function cell phone. And then saying that for all other blue dots, they are the case that represents they don't have a cell phone, just for example. And therefore, this is our training data set. If we are doing some decision tree, naive Bayes or something, then we need to process this information into a model and then building up some rules and building up some graph to make our prediction. However, for k nearest neighbor, when it received the training data set, it said, okay, I got it. I read in the file and I have this information in memory. So no model is being built. It will wait only until a testing data set comes in. So saying that we have a testing data set comes in. This saying that we have a 18 years old that comes in, and we want to make the prediction whether or this person is a red, indicating he has a cell phone, or he does not have a cell phone. And therefore, depending on our k value, this is something I want to show you. If k equals to 1, you will try to find the closest neighbor, which is exactly one neighbor, the closest one who has a cell phone. So I will predict that as, yes, it has a cell phone. If k equals to 3, you need to understand that you will try to find 3 closest neighbors, and you will see that 18, 19, and 16 are the 3 closest neighbors. Since 2 of them are blue, then I will predict this case as the blue label. If k equals to 5 now, you can see that it will include 23, 19, 18, 16, and 12. Since 3 of them are blue dots, then I will consider this as a blue example as well. So now when k equals to 7, it will include 11, 12, 16, 18, 19, and 23. and basically we will, and 24, and basically we will predict this as a red sample. So this is how k-nearest neighbor trying to do in the simplest format. One thing you may notice is that we use odd number for the k is simply because we want to do some voting, and if you use even numbers, then it may have a tie situation, and that may not be an ideal way. So usually when we do k-nearest neighbors, we use the odd numbers to represent the k, and then help us to make our predictions. This is another example that shows you when things are in a two-dimensional space. Of course, like we say, we calculate the distances through the Euclidean distance matrix, and therefore when you try to find the neighbors in this example, you can see that this is our testing data, and by looking into this example, you can understand there are three cases here, three class, and when k-nearest neighbor comes in, you try to find k equals 5. For example, you try to find the 5 closest neighbors, and you will obviously 4 of those are considered as the red sample, so you will predict this x equals to a red class in this k-nearest neighbor example. So this is the simplest idea. And there's, of course, a lot of variation and more advanced versions of the k-nearest neighbor to be discussed. So let's take a look at this. Saying right now we are making a prediction of by class classification, or 3 classes or more. Saying that instead of predicting the class, k-nearest neighbor can also be used to predicting a real value, more like a regression idea. So what it's trying to do is that how do we predict a real value for the testing data? We can find all the neighbors and then use the average value to represent that testing data that we are interested in, and therefore the k-nearest neighbor can be modified into predicting the real value. We can also add some weight into the distance for the voting mechanism. For example, when we are seeing the examples that we have seen earlier, saying this one. Okay, you can see that in this case, k equals to 5, so we find 5 elements over here. However, you can see that the 2 positive cases are actually pretty close to the testing data set, while other 3 negative cases are further away. So if we add some weight mechanism, and that can easily be done, is by looking into the distance. So although we try to find 5 samples over here, we want to add more weights according to the distance. For example, you can say that the closest one will weight of 5. The next closest one can weight of 4. So that even though they're voting on the positive cases, they can have a higher weighted value to put according to their distances. And that is something that can be added into the voting mechanisms. And therefore, this is also something can be easily achieved by using what we call a distance-weighted nearest neighbor algorithm. So this is why we say given greater weight to the closer neighbors. It is actually a very good algorithm, especially when the data has a lot of noise. So noise are considered as outliers. If they are outliers, they are usually not that easily being considered as the neighbors to any regular testing data set. So we can basically ignore those outliers so that it is pretty robust, less sensitive to the noisy data. So how can I determine the value of k, the number of neighbors? That's of course always some research questions. Usually when I apply k-nearest neighbors, I would do a chart, list out all the k values starting from 1, 3, 5, depending on the data set I have. I can go all the way to a really large number and then testing all of those things. It's not that difficult to do, especially if we basically just need a for loop to test out all the case and running the same algorithm again and again, and then be able to record the performance of each operation. In general, the larger the number of training tuples, the larger value of k is. So nearest neighbor classifier can be extremely slow when classifying testing tuples because you need to test out all of the training data set, there's no model. So there's no simple rules to guide you, and therefore you will need to test all the distances. For one testing data set, you need to test the distance with all the training data set. And not to mention, if we want to test multiple k, then you need to multiply that operation into the number of k's that you are testing. And therefore it can be time-consuming algorithm. The simple pre-processing prearrange of the data or creating some tree structure that will be able to reduce the operation performance. So in the basic version of the k-nearest neighbor, I want to show you some synthetic data and then understand what is going on. So saying that based on the data that we have, first of all, we create some random samples based on these design. So we have blue class, we have red class, and we have green class. And of course, this is not some traditional data set that you will see. And that's why I'm saying this is like a more synthetic data to test out the algorithm. So saying that we use this structure creating some random samples, and we have this kind of random sample, you can see that they creating some zone indicating that if I have a testing data set located in here, this is going to fall into the zone of the green zone. So we would classify this one as the green class. And of course, this zone will affect by the number of k. For example, you can see that this green zone over here is kind of surrounded by the blue dots. Therefore, if your k is large enough, this is possibly be eaten up by the zone of the blue zone over here. So that's why what is the good number of k requires some testing. Of course, in this example, k equals to 5, so they have pretty robust zone for each category in this scenario. So saying that if our synthetic data is going to look like this, a circular shape over here, and basically when k equals to 5, we will be able to form 3 zones of the data over here, and this represents the idea of what it looks like. And of course, if we try to change our k number, that's what I'm talking about, when the k will affect the zone drawing. When k equals to 1, it's still very similar to the original design. When k equals to 5, you can see that this will still forming the similar shape, but here is creating some say bridge over here that will make a slightly different predictions over here. And of course, since we know the original design is that with the green it stays inside the circle, blue and the red is going to be the outer circle, this one is probably considered as the better design than this one. Of course, when k equals to 20, you can see that we have a lot of blue dots on this corner. And so when k is equal to a really large number, the red zone on the upper left corner has been eaten up by the blue area, so that it will change into some forms like this way. And therefore, you can really visually see that the variations of the k that will change the prediction process.